Okay, so I'll just quickly repeat what I have just said. So from today onwards, we will study evolutionary dynamics for a few classes, and we will look at the role of mathematical modeling. So as you would have learned in some classes for sure in one of your basic courses, the most basic definition of evolution is changes in allele frequencies. So evolution need not be arrival of a new species. It need not be a new trait that has fully developed. At the most basic level, the definition of evolution is nothing but changes in allele frequencies. You decide which gene to look at and which locus to look at, and you just measure the allele frequencies for a given locus. And if you observe changes in that those allele frequencies in those alleles, then you are observing evolution. Okay. And that's very important. And in fact, this can be observed in a single generation because of many reasons. Okay, so what are the important factors for driving evolutions? So what are those important factors? So those would be, sorry?
Natural selection, driving evolution, right?
Yeah, you're right. Yeah, so certainly natural selection. So how does natural selection happen? What are the necessary conditions for natural selection to happen? I cannot hear you, sorry.
We need variations in the population.
Variations in what?
The population.
Okay, but what about population must be variable?
The phenotype.
So basically, you're right. Basically, let's think of it as you have some heritable traits. It's not just sufficient that those phenotypes are variable; they must also be heritable, right? So any heritable trait, and we should have variation in them. Okay, and this variation is key. What else do you need?
Selective pressure or survival advantage.
Some selective pressure, right? Okay, yeah, some selective pressure. And if you have, what do you get? You get evolution by natural selection. Is it possible to have evolution in the absence of natural selection? Of course, you always need heritable traits.
Yeah, you can, right?
And you always need variation in them. And you can have, it's possible that there is no selection, but under some conditions, you can still have evolution.
Sampling error in small population.
Yeah, by what's called genetic drift. This is true when n finite. Okay. So these are the two sort of dominant ways the evolutionary dynamics happens. So given the mathematical skills we have learned so far, do you think which of the two is easier to understand with the skills that we have learned so far?
The second one.
The right side one, the evolution by genetic drift?
Yes, where there is no selection.
Where there is no selection is easier. Okay. What does anyone think the other way around?
I think the natural selection one is easier. You can add a survival fitness or something, and that would help to model it.
Okay, so let us see. Okay, let us start looking at this. Okay, so let's start looking at we know the tricks of how to sort of, track changes, right? That's what we have been doing in population dynamics, right? So here we have to do the same thing. We just have to carefully track how things are changing. You remember that when we were studying population dynamics, we were considering birth, death, and we were considering how the birth and death was changing density of populations, right? So again, let's look at a population of size n, okay? And let us assume that this population has two genotypes, A and B, okay? So these may correspondingly have two phenotypes. We don't have to worry because we have said, let's look at, allele frequencies only, right? So, and let's say there are two genotypes, okay? And let us assume, so how do we now do, we want to understand how things change over time, right? So you look at what's there at time t, right? At time t, let's make some assumptions. Assume that proportion of A in the population is denoted by PA of T. Okay. And likewise, proportion of B is PB of T. Okay. Now, as you do know, the proportions must add up to 1. So therefore, this must necessarily be 1 minus PA of T. Is it fine? Right now, just so that we minimize the number of indices we are carrying out, since every PB can be expressed as 1 minus P, 1 minus PA, we don't need to write PB anywhere explicitly. We may sometimes write, but remember that everything can now be expressed in terms of PA. And because everything can be expressed in terms of PA, we don't even need to carry that index A. Let's just represent as P of T. Is that fine? This will be 1 minus P of T. Okay. So this is the proportion of two genotypes at generation T plus 1. So now what happens? What happens in a typical life cycle, right? Of organisms, right? So there are zygotes, right? And they become adults. And they in turn give rise to new zygotes at next generation, right? Who in turn then become adults. Is that right? Okay. So proportion of, we have this proportion P and 1 minus P at this stage. And then we want to know what are those proportions in the next time step. This time step can be generation, and we could also consider proportionately smaller the way we did for the population models. For now, let's think of again discrete type dynamics, because often it's a little easier. Okay. So let's assume that when zygotes become adults, there is some chance that some of them may survive, some of them may not survive. So let's denote that by V of A. Okay. So there are some zygotes and they have a chance VA of becoming adults, and if that's genotype A. On the other hand, if they are genotype B, let's say they have probability V of B to become adults. Because obviously not everyone is becoming an adult. Only some of them are becoming adults, and they are VA and VB for two genotypes. And let's assume that once they have become adults, every one of them produces Z number of zygotes. Okay. So let me write this down. VA is the chance of survival of zygotes to becoming adults. It's a bit of poor wording. For genotype A. And likewise, we can define what's genotype B. Okay. So now we are interested in the proportion of zygotes A at time t+1 and proportion of zygotes B at time t+1. So what is that? So let's just look at the proportion. So what we are looking at basically is we want to know what is P at t+1. Is that right? What would that be? So remember that we had a population size of n, and if PA was the proportion, what's the number of zygotes here? What's the number of zygotes here? If you look at the numbers now, number of, it would be n times P, is that correct? Okay, and the number of adults will be n times P times V of A, is that right? And each of them will produce Z zygotes, right? So therefore, the number of zygotes will be n times P times V of A and Z. That's for A. That's for type A. Is everyone fine?
So here P and PA and PB represents the number of like fraction of
Proportion, yes.
zygotes, right?
Yeah.
Okay.
Yeah, that's right. Yeah. This is for the genotype A. And if we were to now write a similar expression for genotype B, at t+1 will be, n remains same, P becomes 1 minus P, right? And then VA becomes VB. And then again you have Z. So it's the product of these four terms. Okay. So this is the number of genotypes of A at t+1. This is the number of genotypes of type B at t+1. So what's the proportion? Proportion is basically the ratio n P of T. I'm inserting that T back here. VB times Z.
Could you mention what's Z again?
Z is the number of zygotes produced by each adult, each surviving adult.
Sir?
Yeah.
How are we accounting for the population that is being carried over from the previous generation? Can you explain that? I didn't.
How are we accounting for what? Sorry.
How are we accounting for the adult population that is carried over from the previous generation? Because here the number of zygotes is n times P, right? But then.
Yeah. So the number of zygotes are n times P. Yeah, you're right. That's why we are making the standard assumption that every adult of the previous generation is now dead. Okay. So we're only now interested in the new set of zygotes that are formed. It's a very good point. Okay. Just like the standard discrete time models.
Yes, sir.
Any other doubts? So basically just, keeping track of everything here. Nothing much complex that's happening. So I can cancel n in every one of these. I can cancel z in every one of this. Is it fine?
One question, why did we assume Z is common for A and B?
You don't have to assume. Actually, you can assume it's ZA and ZB also. Shall I do that? I can also do that. I mean, we can, yeah. Actually, there was no good reason to do that. Huh?
But
Maybe
this
it's-
cancellation won't work. in that
Yeah,
case,
yeah,
right?
we will not cancel. You're right. Yeah. I can
Okay.
actually keep it. So maybe, shall I just keep it then? I can actually make it general only. Okay. I'll assume it's ZA. So it's either ZA. I'm sorry, it's just becoming so cluttered. Okay. So this is ZA. So this now becomes ZA, this becomes ZB. So this basically means that type A and type B produce different, number of. Let me also just write this a bit better. It's basically n times P of n times 1 minus P times VA times ZA. Is that fine? Or ZB, sorry. Okay. Any other questions? Thanks. Thanks for this comment. Yeah.
So,
Yeah.
Ultimately, if you're looking only at the reproducing population, we'll say that there's the adults of the previous generation, and after that, they'll give rise to zygotes. Zygotes will, those who survive turn out to be another set of reproductively fit adults, right? So, can't we essentially merge the V and Z terms? Why do they have to be two distinct terms?
Yeah, that's a good point. Another very useful suggestion. Let's just write, sorry, I don't have much space here when I'm writing, so I'm finding it a bit difficult. So let's write WA is equal to ZA times VA. Okay. Then what does W mean? This W of A basically means the number of zygotes times the survival probability. Okay, and in some sense, it's also same as the fitness of A. Is it fine? So we can actually combine the two, and we have done that as you have just suggested. And we can now write down the expression for P of T plus 1 is now basically P of T divided by, again, P of T 1 minus P of T times. Is it fine? So this is the discrete equation that governs how the proportion of genotypes change over time. Okay. Now let's think what is the denominator here. So let's go to the next page now. So let's go to the next page. So what's the denominator? So denominator was basically P of time T times omega A plus 1 minus P times omega B, right? So basically in the entire population, right, at time T, there was P, there was P proportion of genotypes A, it's multiplied by their fitness, and 1 minus P of B, and it's multiplied by their fitness. So it's basically a weighted average of the fitness of two genotypes. What does weighted average of any quantity mean? it basically means average fitness. Right? So we denote that by omega bar. Okay, and remember this might of course depend on t. There's a thing that says it shouldn't depend on t. So it's basically the denominator basically is the average fitness of the entire population. So in some sense, what this means is p of t plus 1 is equal to omega a divided by the average fitness of the entire population times the p of t. So this sort of makes intuitive sense, right? So there were these genotypes whose proportion was p of t. And what does this ratio mean? The fitness of genotype A divided by the average fitness. What does this mean? This is sort of
Relative fitness.
it's not okay. It's not quite relative fitness. It's a sort of yeah. So relative is you have to compare with some sort. You have to compare with B also, right? It's sort of normalized fitness. I mean, I wouldn't call this relative fitness. Okay. Okay. But relative fitness will come into picture very soon. Okay. But in the sense of intuitively what you're thinking, you're absolutely right. Okay. So you look at the fitness compared to the average fitness of the entire population, and then you multiply it by the current frequency. So well, maybe it's okay to call it relative fitness, right? Yeah. What this means is that if omega a is more than the average, what happens? P will increase, right? If this quantity, actually, maybe I think you're right. Maybe you're right. No? You can call this relative fitness. Although I was preferring to call another quantity relative fitness. We can discuss that. Okay. So what this basically means is that if omega a is greater than the average fitness of the population, that means that P of A increases. Else P of A decreases. Do all of you agree with this? Very simple statement. This sort of provides a very simple mathematical way of saying what is sort of what we all learned intuitively in the evolution, right? If the average fitness of a genotype, if the fitness of a genotype is more than the average fitness, of course it has to increase in the population. Okay, that's what this simple mathematical equation captures. Now let's look at changes. You remember that we were also very much interested in understanding changes, right? So what is the change in the frequencies? You just do this. How much change happened in one generation? Okay, so that would be, look, going back to this equation, it will be omega a p of t divided by omega bar minus p of t. Okay, so we can take p of t as a common factor here. So we have p of t, and then the denominator will be omega bar, which is the average population fitness. And then what we have is omega a minus omega bar. Is that correct? Okay. Again, at every step, it's useful to interpret. So is the change in the genotype frequency of A. This change will be positive when omega A is greater than the average fitness of the population. Makes sense, right? Okay, so again, we are on right track. So now, but let's just remember that omega bar is nothing but this expression. Okay, so let us substitute, omega. Let's try to simplify this omega A minus omega bar term. Omega A minus, I'm basically using this now, this expression, from P of omega A minus 1 minus P of omega B. Okay. So in the first term, let us take omega as a common factor. So what we have now is 1 minus P into omega A minus 1 minus P into omega B. Now 1 minus P is a common factor, so we can write that as 1 minus P into omega A minus omega. Is everyone with me so far? So a lot of simple algebra. So now let us substitute this omega A minus omega bar in this equation, in the numerator here. So therefore, we will have delta P is equal to P of T. Omega A minus omega bar will be 1 minus P of T times omega A Is everyone fine with this? All the algebra so far? Any questions?
Yeah, I was wondering if omega bar changes with time, or is it like a constant?
Yeah, so I did briefly mention as we look at this equation, right? So omega bar is P of T, right? Which depends on time. The proportions are changing over time, times omega A plus 1 minus P of T times omega A. So P does change with time, therefore omega must change with time, right? Do you agree?
Alright, so yeah, so in all of these steps, it's actually omega of t. Omega at time
Absolutely,
t.
absolutely. As earlier, yeah, it might also depends on time. Yeah. So I'm going to drop T everywhere to make it uniform and to sort of reduce the complexity of notations. P into 1 minus P. Can omega depend on time?
Yes.
Yes, there you go. So basically every term here can depend. Okay. Does that look a bit familiar, this equation?
Logistic equation.
It looks like logistic growth equation, right? Where the population density is now replaced by the proportion of, one type of genotype. Okay. And it's also very clear the rate of change. So basically, if I think of it as the rate of change, because I can just divide by one time unit throughout, I get the rate of change on the left hand side. The rate of change of genotype frequency is given by P into 1 minus P times omega A minus omega B, which is the sort of differential fitness. Okay, is that right? This entire term can be interpreted as differential fitness, between A and B. Okay, so it which basically means that omega A is greater than omega B, the rate of change of genotype frequency A will be positive. If omega A is less than omega B, then it will be negative. Does that make sense? Okay, so let's look at simple implications of this simple equation. So what does this imply? We can again think of equilibrium points here, right? Which are the equilibrium points? Whenever delta P is 0, we have equilibrium, which means either P star is 0. Remember, P star is basically A, P of A, huh? Or 1 minus P is 0, which means P star is 1, which means the entire population has genotype, genotype B. This basically, P star A 0 is same as saying PB star is 1, right? So the entire system has only B genotype, or you have the entire system has only A genotype. Those are the two equilibrium points of this simple expression we have found so far. Okay. And we can also think of stability if omega A is greater than omega B. What does that mean? This entire term is like the intrinsic growth rate term, right? If you remember, we had this term R in the logistic model, right? If R was greater than 0, what was the stable equilibrium? X equal to K,
1.
right? Or in this case, P is equal to 1. Yes, stable. On the other hand, if PA is equal to 1, and that you can just, you don't have to do the formal derivative analysis. You can just arrive at this by looking at the slope, just by graphical analysis, right? So for example, if this quantity is positive, the right hand side will now look like this, right? So therefore, these two are the fixed points, and therefore things will move this way. On the other hand, if R was negative, the right hand side will look like this, right? And therefore we have it exactly opposite result. Is that fine? Any questions so far? So basically, by thinking about just one generation changes in the allele frequencies, we are able to make projections for the long term. Okay, what will be the long-term consequence of this evolutionary dynamic by looking at what happens within one generation? Of course, the assumptions we have made a whole bunch of assumptions while writing this and while arriving at this. While writing the equations, we have made assumptions like non-overlapping generations, and infinitely large population, and so on and so forth. We have made the same set of assumptions that we made for writing population models. When doing stability analysis, we have added a few more assumptions that are not necessarily very evident to you. Okay. For example, as people have already noted down, this is not like the R that we had in the previous instance, right? Because I know in the logistic model, R was a constant. Is R a constant in this case? It need not be a constant because R depends on omega bar. Omega bar itself depends on P, right? So it's a bit more subtle here. So omega bar itself depends on P, which is a time dependent quantity. So R is time varying here. However, this analysis will be still valid as long as the sign of R doesn't change over generations. The sign of R remains same over generations, then R will be still fine. Now this, whatever we just arrived at will be still fine. Okay. So it's important to keep that subtle distinction in mind. Okay. And do you expect R to change sign? When do you think R will change sign? The sign of R will be dependent only on the numerator, right? And does the denominator contribute to the sign of R? It doesn't.
It's always positive.
It's always positive, right? So only numerator will. So as long as omega is greater than omega B, then we can make some statements. But I can make a more accurate statement. This is not the most. I think whatever I just realized that what I wrote was really not the most accurate statement. And I want you to think about this a bit, and I think it will be clear when we do the next analysis. Okay. Okay. So far, does everything look fine?
I had a question about the assumption.
Yeah.
So we said that Z is the number of zygotes produced by each adult. So in this case, are we considering only females in the population, or is it like?
That's a very good question. So yeah, that's like even in the population model, that's one way to think about this. Or you can also think of this as an asexual population. There are two ways to think about it. Yeah, the same set of assumptions we made when we were thinking about population dynamics also holds true.
And how do we determine this fitness? Like if we are assuming it over here.
What is the value of omega A? Is that your question?
Yes. Like how do we measure
that will
it?
depend on the genotype A, genotype B, and let's say you're looking at a specific context, and then maybe empirical data will tell you what omega A, omega B must be, and those will then tell you. For example, one simple example I can give in the current context is there are 2 strains of a virus, only 2 strains, let us say, okay, and then omega A will correspond to the fitness of that strain, and omega will correspond to fitness of that strain. So how do you measure in real world population is always a complex question, difficult question. Okay, so one has to do controlled experiments, and maybe you do some observations and then infer omega A. So it's always a challenging problem. How exactly do you obtain values of omega A, omega B is always a difficult question. But in some, so there are 2 ways to think about this. One is you're applying it to a specific context where you directly measure in an experimental setup, and as we will do in some of the later classes, we will also sort of think of explicit scenarios where we can come up with what is the structure of omega A and omega B.
Okay.
But we are looking at a very general scenario now. So therefore, we have not made too many assumptions about, we haven't really figured out what is omega A, omega B. We will do some of those in the later classes.
And you also said that they may also vary with time, right?
Yes, absolutely. Yeah.
Okay.
I've been very interested. That's why we'll discover some of them over time. Yeah.
Okay.
We will learn about them. Yeah. Okay.
Sir, as per the formulation of omega, it is like V times Z. So the dimensions of omega is number of, the population number. Is that, so typically what is a dimension for fitness?
It's the number of offspring who survived adulthood.
So, okay. Okay.
And you're dividing it by omega bar, which is also the same
Yes.
dimension. So it becomes
Correct.
a dimensionless quantity. Okay, excellent. So let's now move on to a slightly more then next sort of slightly complex scenario, which is the case of diploid organisms. Okay, so let's account explicitly for what happens in diploid organisms. So in diploid organisms, let's say if we look at one locus, it can have, let's say, allele A and allele B. Let's say these are 2 possible alleles. If that is the case, there are 3 possible genotypes. So now these are the things I am assuming you must just know. Okay, if you don't know, you will have to revise this. There are 3 possible genotypes: AA, AB, BB. So one of them comes from one parent, the other comes from the other parent. Okay. Okay. So basically, both the parents can have the allele A, in which case they contribute, rather both the parents contribute the same allele, in which case the offspring will have AA. Both the parents contribute allele B, then the offspring will be BB. however, it's possible that they contribute different alleles, therefore the genotype will be AB. So there are 3 possible genotypes in diploid organisms. Okay, and just like what we did with assumption of so in the previous case we did not really worry about the we were describing A itself as the genotype. So one way to maybe think about this is A is probably a phenotype that we are measuring and looking at. The other way to think about this is maybe this was a haploid organism, okay, an asexual organism, and that's why this simplification was possible. Let us say that now I'm actually interested in a diploid organism where there are these 3 genotypes, and all the 3 genotypes may have their own traits, and therefore they may have their own fitnesses, right? So let's denote them by omega AA, omega AB, and omega DB. So each genotype has its own fitness. Okay. So then how do we now go back and rewrite this? So here is the thing. So think about the following. When we wrote down this equation, what was A? We just were looking at how the proportion of allele A is changing over time, right? So now we can still use the same formula that we have derived here, but for when we are thinking of alleles only. For these 2 alleles, I can still write the same formula. Okay, so please convince yourself that is indeed the case if you are not convinced. Except that the omega A will depend on how the genotypes are distributed, and omega B will depend on how the genotypes are distributed, and likewise omega bar will depend on how genotypes are distributed. So what is omega A? Omega A basically is, okay, the probability that an allele A, basically omega A is the fitness of allele A, right? Allele A will be fit either when AA reproduces or AB reproduces. Do all of you agree? Right? Allele A will be happy, happiness, and they'll be fit when either of them, reproduce. So if an allele A interacts with another allele A, which has a probability P, then you will get the genotype will be AA, and therefore the corresponding fitness will be omega AA. On the other hand, allele A may also interact with allele B with a frequency 1 minus P, with a probability 1 minus P, in which case the corresponding fitness will be omega AB. Okay, so therefore omega A can be written as the allele frequency times the corresponding genotype frequencies. Okay, so in the previous case, omega A's, we thought of them as constants, and we also briefly considered the possibility that it might also change over time. And we knew that omega bar depends on P itself, right? But what this shows is that the moment you go to diploid organisms, omega A itself can depend on the proportion of alleles. Okay. Likewise, omega B is the fitness of allele B, and that would be 1 minus P is the probability that an allele B will meet with allele B, and they will reproduce with this fitness. And then allele B can also meet allele A at the probability P, and will reproduce with the probability omega AB. Is that fine with everyone?
Here, what omega AAAB represents?
Omega AA is the thing. At the end of the day, reproduction happens by individuals, right? Okay, individuals, genotypes are the ones that actually go from one generation to other generation. An individual having a genotype AA has a fitness of omega AA is the interpretation of this.
Okay. So individual fitness of each phenotype.
Each genotype which may have a corresponding phenotype.
Okay. Fine.
And that, of course, that exact phenotype, genotype matching will depend on various factors. For example, if there are, dominant recessive like alleles, then the kind of fitness you observe will be different, and so on and so forth. Okay.
A small doubt. I'm
Yeah.
really confused. The omega AB, there'll be 50% chance that the reproduced the next generation will be AA or AB, right? So shouldn't we divide by 2, or is it fine? Like
So it's a good point, but I have already taken sort of, the thing is the number of individuals, see AB also can occur in BA, right? They can occur in 2 ways, AB or BA. So I had effectively taken care of that by not writing 2 times here. If I had not taken care of, I would have written 2 here.
okay, thanks.
Right? Yeah. So that 2, you're right. Only half of them contribute to allele. It's basically half, but there's actually a 2 here also. They get cancelled. It's a good point. Sorry, I didn't explain that. Okay. So now with this, can we now write down how this will look now? Okay. So with this, how will the numerator look like now? Omega A minus omega B. Will be now. Let's pull together maybe P terms. Okay. So there are 2 P terms. This and this, they will come in opposite signs. So P times omega AA minus omega AB. And then we have, let's maybe do a minus sign. Minus of 1 minus P omega BB minus omega AB again. Is that fine? So this is the numerator. And the numerator can be simplified further. Okay. Let us do the following. Okay. Let us take the P terms together. So there is, if I expand this term, the first term will have no P, right? It will be just minus of this term. The other term will be minus times minus P times this term. Okay. And then let me now pool together both the P terms here. So what happens? So I'm pooling the P terms here now. Omega A, omega AB, they are coming from here. And then there's the plus term here, plus omega BB, and then a minus of omega AB. Is that correct? Minus of omega BB minus omega AB. If I make algebraic mistakes, please let me know. Okay. This is what we have now. And let us write this in the following way. Let's take this entire thing as a common factor outside. So I have omega A plus omega BB minus 2 omega AB. Okay. And then I'm taking this entire thing out. Okay. So then what I have is 1 minus omega B minus omega AB divided by this term. I hope I have space to write.
P minus.
So that should be P minus, right?
P minus.
Is it correct? Yeah, you're right. Thank you. This entire term is now this. Thank you for paying attention. Okay. Yeah. This is fine. So far is everyone fine? Now let's now plug this entire thing in the delta P equation. So therefore what we have delta P is equal to P into 1 minus P into P minus some P hat times, let's also say omega hat. Okay, so where I will just describe all these things now. P hat is nothing but omega BB okay, that's P hat. And what's omega hat? It's basically omega AA plus omega BB divided by omega bar. Is that fine? Is everyone fine with this? Okay. So now look at this equation, right? This is for a diploid organism. We're looking at how the allele frequencies A and B are changing. We're not looking at how the genotype frequencies are changing, but we're looking at how the allele frequencies are changing. This is the rate of change of allele frequency A. P stands for PA, as we have been using. So what are the now equilibrium for this? The possible equilibrium are P is equal to 0, P is equal to 1, right? And P is equal to P hat. Do you agree? There are 3 possible equilibria, not 2 anymore, right? However, the P0 and 1 are totally fine. What does P1, P0 mean? You know, everybody is allele B, allele B now. Okay, everybody, P hat would mean everybody is allele A. P hat is equal to, P star is equal to 1 means. P star is equal to P hat means that it's an intermediate value. Because P can't be greater than 1, P can't be less than 1. So it has to be an intermediate value. Then only P star is equal to P hat makes sense. Do you agree with that point? Okay, and this equation is quite remarkably similar to the question I had given in the exam, right? Which had 1 minus x, px into 1 minus x into 1 plus x kind of a form, except that now it continues in the same sort of it has here p has to be positive only, so you don't have that a negative value of x possible. Okay, so there are now 2-3 possibilities, right? Okay, now this third equilibrium is possible only if p hat is less than 1 and greater than 0. Is that right? Otherwise p hat is meaningless. Okay, it's not a useful equilibrium at all for us. Okay, so let's see, let's see when is this true. So first and foremost, if you want to have p hat greater than 0, what is the condition we need? So condition we need is that p hat greater than 0 implies that the omega bb is greater than omega ab, right? In addition, this entire thing must also be positive, right? What does that mean? Now, what does it mean? Omega AA plus omega BB divided by 2 must be greater than omega AB. Is that right? If these two are true, then p hat will be greater than 0. Okay, it doesn't guarantee that p hat will be less than 1, When will that be true, by the way? We also want that to be true, right? For that to be true, p hat must be less than 0 means that the numerator must be greater than denominator. Also, it's the other way around, right? The numerator must be less than the denominator. Isn't that obviously true in this case? So the numerator is omega bb minus omega ab, right? So let's look at the denominator. Denominator can be written as this.
There will be p hat less than 1, right?
Sorry?
This condition, numerator less than denominator. P hat less than 1.
Oh, yeah, that's understandable. Yeah, I wrote it wrong. Yeah. Was it the mistake you were pointing out?
Yes.
This must be, so let's look at the denominator here. We want this to be greater than pb minus omega ab, right? Under this set of scenarios, right? So, but just note that this entire thing and this entire thing can cancel out. So p hat less than 1 requires you to do the following condition: omega a must be greater than omega ab. Is that fine? Okay, so if you want both p half had to be greater than 0 and p half had to be less than 0, we end up with two conditions. I'm going to write them here. This one and this one. And what does that mean? What is the interpretation of this? You would know that omega a and omega bb are together called homozygotes, right? Is that right? And omega ab is called, okay, omega a, omega b are the fitness of homozygotes, and omega ab is the fitness of heterozygotes. So what do these conditions put together mean? These conditions means that the fitness for if you want to have, if you even to have an existence of this intermediate equilibrium, one way to achieve that, we are not showing this is the only way, by the way. One way to achieve that will be that fitness of homozygotes is greater than fitness of heterozygotes. Does it make sense? And when the fitness of homozygote is greater than heterozygote, what do you expect? So what are the homozygotes here? AA or AB, right? AAA or BB, right? If those are fitter than heterozygotes, can heterozygote be the eventual, can it eventually stay in the population?
It will be an unstable equilibrium.
So this means that either we can just intuitively argue, right? PA is equal to 0 or PA is equal to 1 or stable equilibrium in such a case. Okay. Okay, now I will leave the second part of it. You can actually work out by just flipping the signs, by the way. If you go back to this, we started off saying for p hat to be greater than 0. If you're able to see this now, for this to be 0, we assume that both numerator and denominator are positive. We can also flip this, right? We can just flip these two conditions. Numerator is negative, denominator is negative. If you use that condition and if you again apply these two rules, you will get the exactly opposite criteria. Alternatively, we can have the following. We can have omega AB is greater than omega BB. Omega AB meaning the fitness of heterozygotes is greater than that of homozygotes. If this condition happens, then again P star, you should verify this for yourself. Follow this, and intuitively, what do you expect now? There are three equilibrium, right? 0, 1, and this intermediate P hat value. What do you expect in that case?
Heterozygote would have stable
P
equilibrium.
hat will be stable equilibrium, meaning the allele frequencies will be an intermediate value. Therefore, we also have heterozygotes in the population. Okay, and PA is equal to 0 or 1 will be unstable, or both in fact unstable. Okay, so this is where I want to stop today. I think we have done enough algebra for today to sort of show that just simple algebraic equations can help you understand and provide some interesting insights on how in both haploid and diploid organisms evolution works, right? So we will continue from here in the next class, but still let's go. If you go back before I conclude, I want to go back and see within all of this, where are we? What are we studying in this qualitative description of evolution? Are we studying the evolution by natural selection, or are we studying evolution by drift here? So far, what did we do? So because we assume that omega A's, that the two genotypes are in the multiple genotypes, they can all have their own fitness. They're not necessarily equal, right? Which means there can be selection pressure, right? So the left-hand side is what we wrote equations for today. Okay, so we are, when doing so, we have of course used this fact, right? We have incorporated this fact when we were writing equations, right? We have incorporated this fact when we are writing equations. When did we ever use this in our any of our calculation? Did we use any of this variation of heritable traits?
No.
We know that these three are required for evolution by natural selection, right? Did we use the variation? How did the variation part arrive in our equations?
A-B variation?
Sorry?
Isn't like phenotype A and phenotype B like variation? Doesn't that count as variation?
The very fact that there are two types, no? Does that count as variation? Yes, it does. In the most basic way, it does. For example, P is equal to 0 and P is equal to 1 are the cases when there are no variations, right? If everybody is same genotype, or if everybody has the same allele, then there is no variation. And again, if we go back to our equations, what does it predict then? Will there be evolution? Delta P is evolution, right? Change in allele frequencies, right? Will there be evolution when P is equal to 0 or P is equal to 1? No. So when you have no variation, you will have, when everybody is same, you will have no evolution. That is actually very nicely captured in this term itself, right? So in fact, what we can mathematically show that when there are two alleles only, two types of genotypes or two types of alleles, P into 1 minus P is actually same as mathematical variance. Okay. And in fact, that's also sort of, is intuitively clear if you look at this term, right? When either P is equal to 1 or P is equal to 0, we have no variations in alleles or genotypes, right? And when is the allele variation maximum? When you have two types, when P is equal to half, right? That's when you have equal number of A's and B's. Therefore, you have maximum variation in the population. In fact, this P into 1 minus P will be maximum exactly at P is equal to half. Okay. So in fact, so this equation nicely captures. So evolution by natural selection. So let me go to maybe the last slide again. Write this. So delta P is equal to P into 1 minus P into omega A by omega bar, right? So the left-hand side is changes in allele, genotype, or phenotype, or anything that you have chosen to measure, changes in that comes from variation in traits multiplied with, what is this term? differential fitness between alleles, genotypes, types. So basically, whatever we were writing, we have been thinking about evolution in a verbal sense, is basically if you just multiply the two things, right? Variation in allele, variation in the traits, and the differential fitness. If you just multiply the mathematical equivalent of those two, what you get is changes in the allele frequency, which is the evolution. Okay, yeah. So I'll stop here today, and we will continue on Friday. Thank you. So if you have any questions, you can stay on if you want it. Yeah, I'll be around for a few more minutes. Yeah, Tarun, you have a question?
Could you, in the previous page, could you go over why the stable equilibrium is p equal to 1 or 0 in the first case and p is equal to p hat is the stable equilibrium?
Yeah, I can do it. Yes. So okay. So far until this equation, are you fine?
Yeah.
You agree there are three equilibrium: p0, 1, and p hat. Okay, and the p hat is relevant only if p hat is between these two, between 0 and 1, right? And omegas can take any value. There is no guarantee that p hat has to be between 0 and 1. So therefore, what I have done, these two algebraic steps. Are you able to see my mouse cursor?
Yeah.
So this condition told me that the homozygote BB must be fitter than the heterozygote AB, right? The second condition, that p hat must be less than 0, told me that again the homozygote AA must be greater than heterozygote AB. So if both, at least both of them has to be simultaneously true. Okay. Do you agree with that? Because p has to be between 0 and 1. It can't be above. Okay. So it means that both the homozygotes must have a higher fitness than the heterozygote. So then p hat is now guaranteed to be between 0 and 1. See, this alone doesn't tell anything about stability. Okay. Here now I was using an intuitive argument following this. Now we have three equilibrium, 0, 1, and so let me try to write this here now. We have now three equilibrium, right? Let's look at this line. P, we have 0, and we have 1, and we have some p hat here. So I'm now just entirely using an intuitive argument. I'm not using a mathematical argument like we have done in the past to look at slopes and so on. I'm just using an intuitive argument that this is all A's, this is all B's. Both all A's and all B's are fitter than the the intermediate allele frequency, which will give rise to heterozygotes, right? So these two extremes will not have heterozygotes. So on all alleles being 0, all being A, all being A, this is all being A, this is all being B. Neither of them will have heterozygotes, but those two are fitter than this intermediate allele frequency, which has heterozygotes. So I just used intuitive argument to say that therefore the stable equilibrium has to be 0 and 1. Okay, but I have actually not used, you're right that I actually did not use any mathematical argument to arrive at this, but it's actually fairly straightforward to do so also, right? Let's look at this, let's plot this. What is omega bar? Omega bar is basically omega A plus omega BB minus 2 omega AB, and we have taken that to be positive, right? Here. So this is a positive quantity, omega bar is positive quantity. Okay, and then we have p into 1 minus p, and we have an intermediate function p minus p hat. Okay, so now how will this function look like when omega bar is positive? That you can just plot. Let me know if I'm right or wrong. So if omega bar is positive, this will look like this. So this is the left-hand side. This is the function f, which is the right-hand side, sorry, f of p. This is how it will look like if, these conditions are satisfied. This is how this function will look like. Okay. So now if you look at 0 as the, so you should, that is something you should verify. It's not very evident if you look at the equations how the graph will look like. So you should just verify it for yourself. So if I make a perturbation here, it's a negative growth rate, therefore it will actually go back. On the other hand, if I make a perturbation below 0, it actually will go up because it's positive growth rate there. So basically 0 and 1 are stable equilibrium for when omega hat is positive, and this is an unstable equilibrium. Okay, so basically whatever we intuitively argued, because homozygotes are fitter than the heterozygotes, they have to be stable, also happens to be consistent with the mathematical stability analysis. We can do exactly the same thing when the conditions are flipped. I showed you the other alternatively, we can also have these two that will maintain between these, between 0 and 1. In such a case, it will look like this. 0, p hat, 1. Okay, this is f, the right-hand side, the entire right-hand side here. And what you will note from this is, any perturbation from 0 will actually grow here, and any perturbation below 1 will also come back. Therefore, this is the stable equilibrium, which means the heterozygosity is the stable equilibrium. Okay. One point I want to make clear is, there is actually initial condition dependence here, whether you achieve all A or all B. So this is basically all B, right? This is basically all A. No, only allele A, right? So that depends on the initial condition, whether you start close to 0 or whether you cross close to 1. Is it clear, Tarun?
Yeah.
Any other questions?
So what happens when WAB is greater than WAA but not WBB? Is that case even possible?
Will P hat lie between 0 and 1 in that case?
Oh, okay.
Yeah, that will give you answer.
Yeah, cool.
See, for example, if omega BB is greater than omega AB, but if the opposite is not true, if omega A is still less than omega AB, then you have a hierarchy, right? Omega BB is greater than omega AB, greater than omega AA. So clearly, all B will be the equilibrium, stable equilibrium.
And this shift, as you were saying, that it depends on the initial condition. If we have a P cap over here, so even if omega AA is greater than omega BB, so if we lie on the other side, so that would.
So in this, for this case, yes, it's possible that both the both these P is equal to 0 and P is equal to 1, meaning all A and all B are both stable states, even when, let us say, homozygote A has a higher fitness than homozygote B. You're right.
Yes.
Absolutely right. Yeah. That will not happen in haploid, right? That's the interesting prediction of this model. If you have a haploid population, if allele A is fitter than allele B, allele A will always get fixed. Right?
Yes.
In diploid, that's not guaranteed. It depends on the initial condition. So it's good that you asked this question. I forgot to emphasize this point. I was focusing more on whether heterozygoty will survive or not. But it's also a really, really good point. So something, difference, very interesting difference between haploid and diploid cases.
So, sir, this was a diploid asexually reproducing population, right?
What does it make sense? Diploid asexually reproducing?
Exactly, it doesn't. So
Ah,
I
it
mean,
doesn't.
even
So
if,
it's so diploid is sexually reproducing.
okay.
Why did you think it was asexual?
No, but we did not change the notations, right? So
Yeah,
this
but the
still
framework still
means-
holds true, no? Why should we change the
So-
notation?
right. Okay.
Yeah, think through all the steps. It's a bit, it might appear simple, but also there are some subtle issues here and there that I wouldn't have emphasized.
Can you restate your last argument that you differentiated between haploid and diploid, and then you said that, like, I asked the question relating to if the haploid or diploid is more superior than the other one.
I did not say haploid is more superior
No.
than the other
Like
one.
the differentiation that you made.
So let's go back to the previous this one right here. This is a case of this is the perfect case for haploid. Haploid. Organisms, right? So this actually, by the way, this equation is more general. This can all be applied to, this can be applied as long as there are two types. I don't care how the two types come from. This two type can come from sexual reproduction, asexual reproduction. It doesn't matter actually. As long as I can quantify the fitness of two types, omega A and omega B, this equation is true. This equation. Now the consequences will require some assumptions. So for me to go from here to assume that there are only two equilibrium, that requires the assumption that there is no P dependence between omega A and omega P, right? Right? That assumption and the assumption that omega A and omega B are constant and they do not depend on P, for example. If I add all those few assumptions, okay, then I will get that there are only two equilibrium, which is P is equal to 1 and P is equal to 0. Okay, it is actually possible to construct scenarios where even in haploid systems, you can have an intermediate stable equilibrium. It's entirely possible, by the way.
Okay.
All that I'm trying to say is that if the allele fitness is fixed, okay, if it is if the fitness of allele A is a fixed quantity, doesn't change over time, doesn't change with P, likewise with B. In that case, I can just compare it and I can arrive at the conclusion that we have only one or two outcomes, 0 or 1, right? It diploid, even if the genotype frequencies are constant, omega A, omega AB, omega BB, that will lead to a the frequency dependence of the fitnesses. Okay. Now that I have used the word, let me just say it anyway. When omegas depend, the fitness of an allele depends on the fitness of other alleles present in the population. Okay, that's called frequency dependent system. Okay, and the corresponding selection called frequency dependent selection. Okay, so in diploid organisms, that naturally emerges. There is a frequency dependence in the fitness of alleles. Okay.
Yes.
And what I told was, even if the homozygotes AA is fitter than homozygote BB, it is possible that which means that if everybody was AA, right? That population has higher fitness than everybody being BB, right? Even in that case, it is possible that everybody being in having the BB is still a stable state, at least for local perturbations.
Okay, this is for the reason that the fitness of our allele depends upon the other.
Exactly. Yeah, that creates an intermediate unstable state, and that separates. That allows for existence of two stable states.
Okay.
So this is another case of very simple case of multiple stable states.
Yes.
So I will give an assignment question where this can be applied to some real world context, and I think specifically this I will look up a bit. I think this should be relevant to the case of sickle cell anemia disease. So I'll try to give an assignment question that helps you think through these in a specific context. Okay, any other questions? Okay, so I'll stop now. So this we will have the lab on Saturday as we had discussed. So Friday, I will just get back to you on. We will have a shorter class on Friday. I'll get back to you about that by my announcement. Bye.
Bye. Thank you.
Thank you so much.
Thank you.